Welcome to the 16th unit lectures of electrical machines 2, and you recall that we were discussing about B distribution last time. We calculate the air gap field distribution B, which was rectangular in nature, and of course, if I want to generate AC voltage, I must see that my B distribution is sinusoidal in nature, because it is ultimately BLB what matters. Now, before I go into that, let us take a little bit of going back and see once again recap in terms of some demonstration how a conductor EMF generates when it moves under a field. For example, the way I will show it in the computer, before that let us try to understand. This is suppose your south north which alternately comes, and the direction of the field here will be vertically upwards, and it is just shown a line on which that conductor will move. Okay. And as it moves, then and then after we get this, I can sketch this, because lines of force going up I have shown positive. So, this is your flux density distribution, but mind you, this is in space in terms of distance from any reference point. You can measure the distance, and this is the flux density distribution, and here is a conductor which if it remains stationary, nothing happens, and this conductor once again it is perpendicular to the board where I am writing, and it is given a velocity. If it starts moving, then voltage will appear, and polarity of the voltage will change as it goes to goes under a south pole looking from the top from a north pole environment. And in between this time, this zone, if since there is no flux density exists, the voltage induced will be 0. So, let us now go to the computer, a demonstration scenario. Here you see that the conductor is marked with a yellow sectional view. It is perpendicular to the board, and it is stationary. Okay. Now, in the next slide, I have shown the B distribution, which is rectangular like this, not sinusoidal, but rectangular, and which one is positive I am calling the lines of force moving vertically up, that I have indicated by positive plus B, and when the lines of force moves down from north to south, north in the upper, south in below, then I am telling it is minus B. So, it is against distance, it is sketched, and there is a single conductor which is stationary. Now, if you allow it to move with a velocity v, then what happens is that whenever this conductor is under a south pole, a positive voltage is induced. Positive means the face of the conductor which is towards me is plus, and the other end which I cannot see is negative. So, once again if I replay it, you can easily see it was cross initially by applying right hand rule, then dot, then once again cross, once again dot. The point to be noted is that the EMF generated in a single conductor follows the same pattern as that of B. Of course, the distance in the second curve can be changed to v into t, where v is the velocity of the conductor. Suppose I am measuring the distance from the initial origin, then the x axis of the rate curve can be changed to v t, indicating that a time varying voltage will be induced. Now, in the next slide, if you see, I have placed two conductors, okay, and they are stationary. Then the first curve, BLV curve, is the left hand conductor voltage I will sketch, and the right conductor, the next conductor on the right, its EMF will be in the last plot down. Now, here once again, if they are stationary, nothing happens, but if you make them move with same velocity, then the voltage induced in the first conductor will be is indicated by this red curve, and in the second conductor it is indicated by green curve, and you see the EMF induced in the second conductor on the right lags the I mean leads the voltage induced in the first conductor. Now, if these two conductors are connected at the back in series, then you will get the resultant voltage, which will be the difference of these two, and you can see. So, this is the red voltage is the voltage induced by this red, and then take the difference and you will get twice the voltage indicated by the blue curve. So, interesting point is that thing starts with a single conductor. Now, this single conductor and these two conductors, if connected at the back, it forms a coil. Incidentally, in any rotating machines, if you understand what is happening to a single coil, other coils will be identical. Only thing is, those coils will be placed in different positions in different slots. So, whatever is happening to a particular coil now, same thing is going to happen to the other coils after some delay of time. Okay. Therefore, it is essential we must know what is happening to a single conductor, then a single coil. After I have come to single coil, I will now define in fact what a coil is, and we know what is going to happen. So, let me now switch over to our desktop, where I will write things and explain to you what do I mean by a coil. So, I am coming back here. Okay. So, that was the demonstration. Now, in my last class, just quickly review that the B distribution in the air gap was something like this, is not, which is this was the B distribution we obtained by a single coil. This is the spatial distribution in B. Mind you, this is distance, or if it is a rotating machine, better I write theta, okay, angular position. Let me explain to you. Now, suppose you are having now whatever I am telling can be understood. These are the iron of the rotor, suppose, and these things are the teeth. It is made of iron, inside also it is iron. Okay. It is a solid block of iron. They may be of course laminated, that we will see later, but the basic structure it is made of soft iron and with some slots. As I told you, we will cut slots, and here in this groove or slots I will place conductor, and these things will be rotating. Okay. Therefore, this can be, you know, as I told you, I will cut it for understanding and display it like this. So, it will become a sort of linear way of understanding rotating electrical machine, that is called the developed diagram. Now, in this rotating machine, what happens is this, how to place the conductor and what is a turn. So, suppose this is the rotor, it has got a diameter. You take a coil, it is a multi-turn coil. In fact, it is a two-turn coil. How I have manufactured it? I have taken a conductor, it goes like this once, comes back, then once again goes back to the same slot, comes back, and ultimately you will have these two free terminals, which I was calling x 1, y 1 or 1 dashed, things like that. If you name, because there will be several coils. So, this forms a coil, and each coil of course is to be named, so as to identify which coil I am talking about. So, numbers are used, 1 dashed. Similarly, there may be another coil which we call 2 dashed. Okay. As for example, another coil, it may be termed as 2 dashed, and these coils I will place in the space reserved for it in a particular sequence, and each coil will have its own free terminals, and they can be connected in series or in parallel, whatever way it is convenient we will do that. So, how to place the coils? Coils will be placed in this way. This is one coil side, it will be placed here, and another coil side will be placed perhaps in a particular slot. I indicated that if one coil side, I must see that this coil span, the difference in distance between the two coil sides should be such that if one coil side at any given time is under the center of north pole, you must see the other coil side is under the center of south pole. Why? Because then the induced voltage between its two terminals here will be maximum 2 BLV. This will be BLV, this will be also BLV. But the polarity of this voltage, if this is plus, this is minus, this one will be, this is minus and this is plus. So, that -2 plus, then once again -2 plus, BLV, BLV, 2 BLV. And if it is a multi-turn coil having n turns, you make n loops and then 2 terminals, this total EMF this side will be n BLV, and this will be also n BLV with opposite polarity. So, that they are added up and will give you 2 n BLV voltage. Now, this B, if it is varying, its magnitude is varying in space, in whichever way it varies, the nature of the induced voltage will be of same shape. If it is rectangular, this voltages too will be rectangular. If the B distribution is sinusoidal, that will be also sinusoidal. Another point I want to tell regarding this arrangement is that this is how different coils will be placed in their designated slots. So, these are called slots. Okay. Now, this portion of this winding, and where will be your north pole, south pole? This is suppose the rotor structure. Similarly, on this there will be an air gap. You imagine there is another cylinder with slots, and that stator iron will produce north south poles when stator coils will carry current. Therefore, this must be seen as this is only rotor I have shown, but it can be made like a stator if you push it like this here. Stator things will look like this way. This stator, here also there will be coils like this. Are you getting me? Okay. And when they will carry current, they will produce their magnetic field. 1/4, if it is 4 pole, 1/4 will become north pole, 1/4 will be south pole, and so on. Therefore, both these things will be present together. Suppose B is produced by the stator coil, you energize like this, there will be coils, and then in the rotor there is slots, there are coils also, and if there is a relative speed between them, then we expect there will be some induced voltage in the rotor. So, these are called teeth, slot, teeth, slot, teeth, slot, like that sequence it will go. So, it may look like there will be several coils. Why there will be several coils? Because I shown that if you are using a single coil, first of all, single coil means you require only 2 slots. Then rest of the space of the iron will be underutilized, that is one thing. It is better try to utilize this space, increase the number of coils, because increasing in number of coils will also ensure that this B distribution will be no longer rectangular, but it will be somewhat stepped like this. That is what I have shown if 2-3 coils are used. And this will be more like a sine wave. Okay. Therefore, people never use a single coil to generate a AC voltage, because if you do that, then B distribution may not be that sinusoidal. Therefore, a group of coils are connected in series and displaced from each other. So, what you do? You place one coil here, another coil next slot, another coil next slot. Suppose 2 coils I put, and I will connect them in series to get the desired voltage generated, which will be more like a sine wave. Now, henceforth in my discussion what I will assume is that the B distribution is sinusoidal, a strong fundamental, and I will neglect the effect of harmonics of B distribution. So, this may be denoted as B max sin theta, where theta is the space angle. It will be like this, and this is the B, and this is space, mind you, space angles. I will consider only the fundamental component. In the mind, I will think that okay, B distribution can be more closer to sine wave. So, only the fundamental component of this different harmonics, I will neglect the effects of those harmonics to begin with. Okay. And for this thing, what will be the induced voltage in a particular coil, we will try to find out. Now, before that, these 2 terms I must tell you. One is called electrical degree, this is very important, and mechanical degree. Angle can be measured in 2 ways, theta electrical and theta mechanical. For electrical, I am not writing the suffix, I will not carry on. So, theta if I write, it means electrical degree. Now, first let us understand what is electrical and what is mechanical angle. Angle is angle. Okay. The angle we know of, geometrical angle, that is the mechanical angle. With a protector I can measure the angle between 2 straight lines like that. But then why it is necessary to introduce another angle theta e? Let us try to understand. Suppose you have a 2 pole structure. I will roughly draw. This is suppose north, this is suppose south, north, south, okay. And you have a single conductor, okay. Let us try to understand, and it is moving with some angular speed or velocity, okay. Suppose it is moving with a speed n rps, and the B distribution we know it will be whatever is the B distribution. Suppose the B distribution is like this, fundamental component of B distribution along this angle theta, where from I am measuring the angle theta. In this particular case, it looks like when the conductor is in this position, it is one half is north pole, another half is south pole. So, south pole zone begins from here, from this horizontal position. So, suppose the conductor was here, and suppose the diameter of the rotor is d. D is the diameter of the rotor, and if I say, and it is a two pole machine, P is equal to 2, number of poles 2, and this north south, as I told you, might have been produced by a coil. I do not bother, just to indicate that okay, a south north pole has been created and stator iron has become magnetized, and now in the rotor there is a single conductor moving with n RPS, rotation per second. Now, what will be the induced voltage? Induced voltage, this is B distribution, the induced voltage, and suppose the conductor was in this position at t equal to 0, Okay. This axis is okay, position in space no doubt, but it now indicates the position of this conductor as time passes. Now, this is angle, suppose this rotates in n RPS, and then you can see the angular speed of this one will be nothing but pi d into n, so much radian per second. This is how the angular speed radian per second is related with rotation per second. You multiply by pi dn, because in one rotation it covers 2 pi, therefore, in 1 second it will cover a distance b is equal to pi dn. I am so sorry, b is equal to pi dn. See, 1 second, one rotation means pi d meter, the conductor moves. In 1 second you are making n rotations. So, velocity in meter per second will be pi d into n, that is all. And omega speed in radian per second will be how much? It will be 2 pi into n, because in 1 second it makes one rotation means 2 pi angle. So, in 1 second it makes n rotations, it will be so much radian per second. So, these are the two things. Why I have expressed V in terms of n? Because the induced voltage does not depend on omega, BLV. So, tangential velocity in meter per second, all that matters. Therefore, if you are rotating the rotor at some n RPS n, and wherever the conductor is, I must know the value of B at that position, whatever position it occupies, and what is the velocity V, tangential velocity, and tangential velocity in meter per second is this one, pi d n. Now, as you can see, this point is important. Suppose I have started counting my time when the conductor was in this neutral position, it has no voltage, but it is going there, that is, it has come here. Then the moment it comes under the purview of this south pole, there will be induced voltage in it. The magnitude of it will be this B, this length of the conductor into this velocity, which is pi d n, is not. So, it will go like this, then it will come here, it will have maximum voltage corresponding to B max. Then once again voltage polarity remains same, but strength is decreasing. It will become 0 here when the conductor will come here in this position, and then when it comes under the influence of north pole, that it will be for so long time here, B reverses. So, induced voltage across the two ends of the conductor reverses. Therefore, induced voltage will be also of this nature. Is not. Therefore, this conductor, when it makes a complete rotation in this direction, and this is suppose omega t. So, omega t was 0, any omega t it was like this, omega t was increasing. Now, when it comes back to its original position, once again it will be 0 and the cycle will start repeating. Is not. Therefore, you see, if you call this theta to be 0 here, pi here, 2 pi there. Similarly, for the induced voltage, this axis I have changed to, this is position no doubt, but omega t. I want to know how the terminal voltage will look like against time. So, this is 0, this is pi, this is 2 pi. The conclusion is, in a two pole machine like this, when the coil makes a 360-degree rotation, your output induced voltage, this axis is voltage in the conductor, that will also make a complete cycle, and that repeats. Therefore, in two pole machine we say theta electrical, this is always electrical, like that I will say, but time is really not ripe to distinguish between mechanical and electrical angle. In fact, in two pole machine, electrical angle and mechanical angle are same. So, theta electrical, which I will not write, only theta electrical is equal to theta mechanical. Why? Because if the conductor makes one complete rotation, the output EMF generated, which I want to see against time, that will also make a complete cycle. Okay, I stop here. In the next class, I will continue with this. That is very important concepts. Thank you.